So we have this equation and we want to solve it for y. First thing I'm going to do is rewrite it in terms of t, just as a personal preference. It doesn't actually matter. And I'm going to write this as t to the 1/2, y to the 1/2, dt. All right. So some of the things I want to do is I want to get things in terms of dy dt. So I want to get rid of that, and I want to get rid of this. So what I'm going to do is I'm going to divide everything by t dt, t dt, t dt. So for the first part, whoop, back to normal. We want, so the t's cancel out, we get dy dt, minus, I'm going to write this as, the dt's cancel there, so I'm going to have 1 over t times y, and then t to the 1/2 divided by t, dt's cancel, is going to be t to the negative 1/2, y to the 1/2. There we go. All right, so now this is where we notice that this is Bernoulli's form. So if this side over here was y to the 0, so this is n. Oh, I'm gonna write this way. This is n. And if n equals 0, then we'd have a homogeneous linear differential equation. If n equals 1, then we just have a linear differential equation, which we can still solve. And if n is something else, then Bernoulli's. So the way we approach this one is, first thing we do is we divide everything by y to the 1/2. So now we're going to divide everything by y to the 1/2, y to the 1/2, y to the 1/2, y to the 1/2. And so now we're going to have, I'm going to say multiply by y to the negative 1/2, same idea. So we have y to the negative 1/2. Now I'm going to change my notation to y prime. Same thing. I know I shouldn't change notation halfway. It's just part of life. Minus 1 over t, y divided by y 1/2 becomes y to the 1/2 equals t to the negative 1/2, right? So now the trick is, I know it's kind of weird when you say trick in math, but true. We're going to say that v equals y to the 1 minus n. So this is the key idea to Bernoulli's. So that key idea of Bernoulli's, you first divide to get everything in terms of just t on your far side, t or x, not the y where you're taking the derivative of it. And so now we say v equals y to the negative 1, 1 minus 1, 1 minus n, where in this case n equals 1/2 because it's minus. Yes. True. Yes, I think so. Yep, I'm going to go with that. So then there's going to be v prime equals 1 minus n, y 1 minus, so we subtract 1 from this, we're just going to get minus n times y prime. There we go. And to be a little bit more nuanced here, we're then going to say this means that v equals y to the 1/2, and v prime is going to be 1/2 y to the negative 1/2 y prime. Right. So now is where some of the substitution and the magic happens. So we have this right here, which is the whole idea of Bernoulli's. And so we're going to say, I'm going to rearrange this just slightly so that we have 2v prime equals y to the negative 1/2 y prime. I know the 1 and the prime makes it difficult. I'm sorry. And so this we have right over here. So it's going to be 2 v prime minus, and we're still going to have the 1 over t. Y to the 1/2 is going to be v equals, and then still we're going to have t to the negative 1/2. All right, so now we've just rearranged this equation so that this is a linear differential equation that we can solve. Maybe red. So I'm going to divide everything by 2 just to get put myself into my comfort zone. So I'm going to say that v prime equals 1 over, I'm going to say v prime, v prime plus negative 1/2, because negative 1 over 2, 1 over t, v equals 2 to the negative, or t to the negative 2, 1 t to the negative 1/2 over 2. There we go. So now we can say this is p of x, and this is q of x, and we're going to multiply everything by u. I'm going to say u, not mu. I know mu is more traditional, but I'm going to use u just because it's easier to write. And so we're going to say that u is already failing, e to the integral p of t dt. So integral of p of t dt equals the integral of negative 1/2 1 over t dt, which we're going to expand to negative 1/2 integral natural log of t dt, which gives us negative 1/2, jumping steps. Integral of 1 over t gives us natural log of t, which we can then rewrite as natural log of t to the negative 1/2. And that's just a log rule. We'll do a plus c because we should. And so now we get e to the natural log of t to the negative 1/2 plus c, which is the same as k, just a constant k. And that's just a log rule because we're breaking up the plus c. This is e to the natural log of t to the 1/2 negative e to the c. And then that just becomes another constant. So then this becomes k. E to the natural log is just disappears. They cancel. They're inverses. Like so. All right. So this is our formula we're going to go for. All right, this is our u that we're going to go for, our integrating factor. So I'm going to bring this down. Oh, probably should do a different color so I can see what's going on. Ooh, light gray. So this is going to be v prime times k. We don't actually need this k because we're going to multiply everything by it. So I'm just going to I'll leave it in for now, but you'll see. T to the negative 1/2 times v prime plus negative 1 over 2t times 1 over t times t. I'm going to write this as 1 over t to the 1/2 times v equals t to the negative 1/2 over 2 times t to the negative 1/2. Does that seem plausible? That might be plausible. All right, so now we're going to rewrite some of this just to make it a little bit cleaner. So it's going to be, also there's what I forgot was the k for all of these. K's cancel, and that's why I meant by they don't matter. They do matter, everything matters, they cancel. So now we're going to have v prime t to the negative 1/2 minus, all right, see what we got here. So this is, A lot. So let's see, it feels like I have something in there I shouldn't. Yes, I totally do. Whoop. I have an extra t in there. So negative 1/2 and then the 1t. There we go. So this becomes negative 1/2 t to the negative 3/2, because this is t to 2 over 2. We multiply together, we get 3 over 2. And then since it's in the denominator, negative v equals t to the negative 1 over 2. All right, we're good with this. Do I want that? I'm gonna write this as 1/2 times 1 over t. I know, same thing, might be important, we'll see. All right, so now, let's see, what do we got here? This should be v times t to the negative 1/2 prime. Now let's check that out real quick. So if we have t to the negative 1/2, and we take the derivative of that with respect to t, we bring down the negative 1/2, and then we do t to the minus 1, which is negative 3/2, which is totally what we got right there. So yes, this is true. So I'm going to rewrite this as v times t to the negative 1/2 prime equals 1/2 1 over t. Yes, then I'm going to square both sides to see, is that supposed to be negative 1/2? Probably negative 1/2. Yeah, I'm good at that. We'll see how this goes. We're gonna integrate both sides with respect to dt. The integral of the derivative is just the original function, so it's going to be v times t to the negative 1/2. My 2's are, there we go. And this becomes 1/2 natural log of t plus c. I think there's supposed to be an absolute value there. I'm going to ignore that for now. So there's probably a justification for why I can. We'll see. I probably should have it in. I'm going to leave it. You're right. Absolute value. All right. So now we're going to multiply everything by, let's see what we have here. Right. So now we're going to multiply everything by t to the 1/2. So we have v equals 1/2 t to the 1/2 over 2 natural log of times natural log of t plus c. And this is a different constant c from the one I've used previously. It's just a constant c. So I'm fast and loose and abusive of constants. And I probably shouldn't be, but I am. All right, so now we have the solution in terms of v, but we don't want the solution in terms of v. We want it in terms of y. So I'm going to come way back up here. I'm going to say that we know that v equals y to the 1/2. So I am going to abuse the benefit of having an infinite whiteboard. I'm going to say y to the 1/2 equals this. And now to actually get y, I'm just going to square both sides. So big finish, grand finale, the parade is this squared. So t to the 1/2 squared is t, 1/2 squared is 1/4, and then we're going to have natural log of t plus a constant squared. Now, since we're not given an initial value, we can't actually find what that c is. But that's okay. This is going to be our final answer. So craziness ensued, I know. Let's recap and kind of look at what we did to get to this final point of insanity. We were given an equation in terms of theta, which I rewrote as t just because I want to, and I think it's easier. And we wrote it in terms of, I'm going to rewrite it over here. We were able to get it in terms of dy dt, which is just y prime minus 1 over t y equals t to the negative 1/2 y to the 1/2. And this we called p of t. This we'll call q of t, just out of convention and how we do these problems. And then we got y to the n over here, where n is basically Bernoulli's. This is Bernoulli's formation of a linear differential equation, which we can solve. And as we said, n equals 0, homogeneous, we can solve. N equals 1, we can also solve. Y equals n, we need this special, I guess, Bernoulli technique. So first thing we do is we divided by y to the n, which reformatted everything. We then said v equals y to the 1 minus n. Substitute in. We also find v prime and substitute that in. We then get v in a form that we can solve. Basically, we get a linear differential equation, and we can solve it by using an integrating factor, which we used and found. After putting in an integrating factor, we see that the first part is just the product rule. So we then combined that, we integrated and solved. So a bit tedious, a bit long, but not that big a deal after you've seen it a couple times. So hope that helped. See you next time.